Alright, so yesterday we learned about all kinds of things you can bounce radio waves off of. We learned you can bounce radio waves off of meteorites, you can bounce them off auroras, like the Aurora Borealis maybe, if you happen to live in Alaska. And today we're going to look at something that you're going to be bouncing radio waves off of a lot if you really get into ham radio. And that thing is the ionosphere. The ionosphere is the primary thing that hams bounce radio waves off of. So the ionosphere allows signals to go, this is what allows signals to go all the way around the world. We're talking like from New York to maybe even Australia or definitely to Europe. And so we're going cross-continental with these things because of the ionosphere. So what happens is the radio signal that you transmit, say that you transmit it from here, what happens is it bounces off the ionosphere. It goes sort of out into space, out into the sky. And this represents all this stuff, the D layer, E layer, F layer. We'll explain those layers in a bit, but this all represents the ionosphere, which is a layer in the sky. And it's not really this big. It's not to scale, but basically the idea is if this is your antenna, your radio signal will go out into space, and when it hits the ionosphere will actually sometimes bounce it backwards. See, it bounces it back towards Earth. And as a result, your signal ends up landing all the way over here on another side of the globe. And that's how we get to talk to other countries with ham radio and with the ionosphere. The signal bounces off and comes back in a completely different place. And this is all possible due to what we call sunspots. So sunspots are spots on the sun that are cooler than the rest of the sun. And somehow these sunspots actually affect the ionosphere, and they cause the ionosphere to reflect certain radio waves at certain frequencies back to Earth. Now, in fact, sometimes signals ricochet off the ionosphere all the way around the Earth, making it back to one's own station. So, for example, the signal might bounce off, signals can actually bounce off the Earth sometimes. It might bounce off the Earth and go hit the ionosphere again, and bounce off the Earth and ionosphere again, etc., 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 until it hits you all over again, which is pretty cool. That means it makes it all the way back to one's own station. And when this happens, your signal is actually delayed a bit because of the long journey, and it arrives back late enough for you to hear yourself sometimes at the receiving end of the radio. This has never happened to me personally, but I have been able to reach stations as far away as Australia with my station in New York, thanks to the ionosphere. So it actually went west across the United States, like past California, and it hit Australia. And this fact means you can talk to people around the world with very little power. You can actually accomplish all this usually using about only 1/10 of the power used by a normal microwave oven, which is pretty cool. However, your results, they might vary with the ionosphere because, as I said, the ionosphere, it depends on sunspots. And it turns out it depends on the number of sunspots there are. The more sunspots there are, the better the ionosphere works at reflecting radio signals. And unfortunately, the number of sunspots doesn't stay the same throughout the year. We have what we call a solar cycle. So the sun sort of goes through a cycle when it comes to these sunspots. So during one period of the cycle, like the peak of the cycle, the sun might have a lot of sunspots all over the place. It's great for ham radio. And then the sun kind of goes into another period where sometimes there are no sunspots at all. There are 0 sunspots. And when this happens, you can still talk to people with the ionosphere. It's just a lot harder because the ionosphere, how well it works at reflecting signals, it all depends on these sunspots. So the sun goes through this cycle, and each cycle lasts for 11 years. It repeats every 11 years. It reaches a peak with a lot of sunspots. It reaches a dip with no sunspots. It starts again every 11 years. Unfortunately, right now, as I'm recording this class in 2017, right now we're nearing the dip of the sunspot cycle. And I think the peak was sort of around 2013 or 14. And now we sort of have to wait a few years until we reach that peak again. But don't worry, as a licensed ham, you can still use the ionosphere, and you can actually still talk to people far away and even in other countries like Europe. It's just going to be a little harder than it would be if there were a lot more sunspots. But don't worry, you can still have a lot of fun. So as we said, the ionosphere is a layer in the sky, okay? It's a layer in the sky that reflects signals. But the layer in the sky called the ionosphere is actually made up of several different layers itself. So here we have the D layer, so the signal might bounce off the D layer and go back. We also have the E layer. The signal can bounce off the E layer and bounce back even farther. And we even have the F layer, and it comes back and it bounces all the way over to there, say. So there are a lot of different layers in the ionosphere. It has different layers. Now, usually the ionosphere reflects HF signals, the high frequency 3 to 30 megahertz signals. But sometimes VHF signals reflect off the E layer in the ionosphere, actually, which is good news for you because you have full VHF privileges as a technician class ham radio operator. So this doesn't happen much. So when it does happen, when VHF signals do reflect off the E layer, it's pretty exciting. It's a pretty big deal. How exciting? Note that word exciting. Exciting starts with the letter E. And that's how you can remember about the E layer, how the E layer is what reflects VHF signals, because it's exciting when this happens because it doesn't happen often. And it's even more exciting, what's even more exciting is that you have VHF privileges under your technician class operator license. So when this happens, you can use the ionosphere to bounce signals. And this doesn't happen very often though, so sorry about that. But don't worry, because 10 meters is an HF band in the 3 to 30 megahertz range. It's an HF band that you do have a lot of access to as a technician class operator. And sometimes that has propagation on the E layer too. In fact, the 10 meter band, the 6 meter band, and the 2 meter band sometimes experience E layer propagation. How exciting. So this doesn't always happen again, so which is why it's called, very exciting. Exciting starts with an E. So 6 or 10 meters can usually provide long distance communications like this during the peak of the sunspot cycle. And unfortunately, 6 and 10 meters, they're a little sensitive. They need a lot of sunspots to work right. So when you're not at the peak of the solar cycle, which we aren't at the peak right now, 6 and 10 meters don't really do anything. So that you can't really bounce them off the ionosphere. And if you get to the UHF bands, the ultra high frequencies, you can kind of pretty much forget about it. 23 centimeters and 70 centimeters, which are UHF frequencies, they pretty much never reflect off the ionosphere, even when the solar cycle is at the peak. And the 1.25 meter band doesn't reflect off the ionosphere much either. And those are actually some facts that you'll need to know for the test. So if you didn't catch that, you can rewind a little bit if you want, and you can write that down. And another thing you'll need to know is that 10 meters, we talked about how 10 meters often uses the E layer, the exciting layer, to reflect off signals. But 10 meters actually sometimes uses the F layer as well. In fact, during the daytime, from maybe between dawn to right after sunset, when the sunspots are good, you can use the 10 meter band to talk to other countries by bouncing it off the F layer. So with that out of the way, that's all pretty cool, but there are a couple random facts that you do have to straight up memorize for the exam because they're hard to understand. So let's go and look at a sample question now that you might get asked about propagation. And the question reads, which of the following results from the fact that skip signals refracted from the ionosphere are elliptically polarized? Huh? Don't worry, we'll explain what that means after we get to this question. Choice A, digital modes are unusable. B, either vertically or horizontally polarized antennas may be used for transmission or reception, whatever that means. C, FM voice is unstable. D, both the transmitting and receiving antennas must be of the same polarization. Okay, hold on, what are we talking about here? Well, the answer to this question is B, either vertically or horizontally polarized antennas may be used for transmission or reception. But that doesn't do us much good if we don't actually understand the question and the answer choice. So let's digest this a little. So elliptically polarized, when the test says elliptically polarized, that's basically a fancy way of saying circularly polarized. Okay, well, what does that mean? So elliptically or circularly polarized signals, basically all you need to know is that they can be received by either vertical or horizontal antennas, meaning either antennas that go straight up this way or that go lengthwise this way. And yes, by the way, there are horizontal antennas that go this way instead of this way. That might seem strange to you, but we'll learn all about those in the antenna section of this course, which comes a little near the end. Right now, we're about at the halfway point. So another thing about this question is it talks about the polarization mentions polarization. So what is polarization? What is polarization of radio signals? So the technician class exam, it actually doesn't really require you to know what polarization means. Even the Gordon West manual, which is supposed to completely prepare you for the exam, it doesn't even bother explaining it. And so in my video lecture, I'm not going to explain it either. It's sort of beyond the scope of this course. So the reason I'm not going to explain it is because all you really need to know is that a radio wave's polarization is determined by the orientation of its electric field. So you remember we said radio waves are made up of electromagnetic fields. They're electromagnetic fields. That is, it's an electric field and a magnetic field. Now, all you need to know is that what determines the polarization, whatever that means, of a radio wave, the electric field somehow that's what determines the polarization. So you should probably write that down in your notebook. It's easier to just remember that the electric field determines polarization than to go into what polarization is and why the electric field determines it, because things do get a little technical. So let's look at the last thing you need to know for the exam about this concept of propagation. So sometimes your signals, they might reflect off the ionosphere in a lot of different ways. So oftentimes your signal will just go in a straight line. It'll just like bounce off here and go back there. But sometimes it goes in all sorts of directions. It might do all kinds of weird, I don't know, maybe not quite like that, but it might bounce in all sorts of weird ways and not quite in the way you would expect. So it might go in all sorts of different directions before arriving at its destination. Sometimes it might do both. It might both go in a straight line, or it might do all sorts of weird things. And you'll receive someone else's signal sometimes multiple times at the same instant. That is, if someone's transmitting from, say, over here and you're over here, part of their signal might sort of split up. Part of it just goes like that. Okay. Part of it does something a little stranger, but so the signal sort of splits into 2 or 3 or maybe more, and they all reach your station at the same time, roughly. So you receive sort of multiple instances of the same signal at the same time. But the effect of this is that this sometimes causes what we call irregular fading of signals, meaning that at 1 second or 1 minute, the other person's signal might be strong, and the other minute it might be really weak, actually. And this is because things are sort of changing with the conditions, and so you're receiving multiple instances of the same person's signal, but things are changing, and now it's sort of the signals are sort of messing each other up, or something's getting messed up. So that's the last thing you need to know. So you can write all this down that I have on the board. There are layers in the ionosphere. Actually, you don't really need to know specifically which layers there are for the test, but you can take a note of the 11-year solar cycle. Actually, that's not on the exam either, but I thought you should know it. And what is on the exam is this stuff here. Elliptically polarized means you can use vertical or horizontal antennas. That's basically what it boils down to. And polarization depends on the electric field. So that's it for this section on propagation. So I want you to go read the Gordon West Manual as usual, learn a little more about propagation maybe, definitely look at the test questions and study. And then once you take the quiz, you can move on to the next section. And we're finally going to be looking at what you may have been waiting for. We're going to look at talking to outer space, talking to the International Space Station, and even talking to satellites and what that all means. So I will see you after you're done.